Hello, my name is Dr. Kenneth Watanabe, and today I will go over the definitive proof of the twin prime conjecture. The twin prime conjecture states that there are an infinite number of pairs of prime numbers p1, p2, such that p1 plus 2 equals p2. The conjecture was first proposed in 1849 when de Polignac made the more general conjecture that for every natural number k, there are infinitely many prime pairs p1, p2, such that p1 plus 2k equals p2. And the twin prime conjecture is a special case of de Polignac's conjecture where k equals 1. Since then, the conjecture has remained largely unproven until Chinese mathematician Yitang Zhang in April 2013 proved that there are infinitely many prime pairs p1, p2, such that p1 plus n equals p2, where n is less than 70 million. And here is a link to his paper. In this presentation, I'll go over a more straightforward proof of the twin prime conjecture, and I'll do this by proving the more constrictive conjecture that for any p sub I and p sub I plus 1, there's at least one twin prime pair between p sub I squared and p sub I plus 1 squared. For example, if p sub I is 3, then there's at least one twin prime between 9 and 25. Since there's an infinite number of prime numbers, and that was proven by Euclid in 300 BC, then there are an infinite number of twin prime pairs. So the first thing I did was write a Python program to count the number of twin primes less than n for values of n up to 50,000, and here are the results. As you can see, it looks like the curve goes up indefinitely, but a graph is not a proof. Before we go into the proof, let's define some functions. Let p sub n be the set of pairs xy such that x plus 2 equals y and y is less than or equal to n, and x and y are odd integers. Vertical bars around p sub n will be the number of pairs in p sub n, and in this case the number of pairs of p sub n is n minus 3 divided by 2. Let lambda sub x be the largest prime number less than or equal to x, and let k sub n be the number of pairs xy in the set p sub n where either the x or y is a composite number, and let w sub n be the fraction of pairs in p sub n where both x and y are prime, and let pi sub 2 of n be the number of twin prime pairs xy such that x plus 2 equals y and y is less than or equal to n. And we can call this the twin prime counting function. So to prove the twin prime conjecture, I use a sieve method. So the sieve of Eratosthenes is an ancient algorithm to find the prime numbers less than n. So starting with a list of numbers, I chose the number 27, and I list the numbers starting with 2 up to 27. And to do the sieve of Eratosthenes, you select the first number in the list, which is 2, and then you eliminate everything that's divisible by 2. Then you select the next number that has not been eliminated, which will be 3, and you eliminate everything divisible by 3. And then you select the next number that has not been eliminated, and that's 5, and you eliminate everything that's divisible by 5. And that's as high as we need to go because the next number in the list is 7, and 7 squared is 49, and 49 is beyond the endpoint of 27. Okay? So all the remaining numbers in the list that have not been eliminated are prime numbers. So I applied the sieve of Eratosthenes to pairs. So for example, I chose n equals 59, and I arranged pairs xy such that x plus 2 equals y for values all the way up to y equals 59. So we have 3, 5, 5, 7, 7, 9, all the way up to 57, 59. Okay. Then I eliminated all the pairs where either the x or the y is divisible by 3, except for this first pair, 3, 5. Okay, so I eliminated 7, 9, 9, 11, 13, 15, 15, 17, 19, 21, 21, 23, etc. And notice that for every group of 3, 2 pairs got eliminated. Okay, so as n gets very large, the number of pairs that are divisible by 3, we can represent that as k sub 3 of n, approaches 2/3 times the number of pairs in p sub n. Okay, and the number of pairs that are not divisible by 3, we can represent that as pi sub 3 of n. That equals the number of pairs in p sub n minus k sub 3. So this approaches 1/3 times p sub n as n gets very large. Next, we eliminated all pairs where the x or y component is divisible by 5, except for this first pair, 5, 7. So we eliminate 13, 15, 15, 17, 23, 25, 25, 27, etc. And notice every group of 5, we eliminate 2 pairs. So as n gets large, about 2/5 of the pairs are divisible by 5. But since 2/3 have already been eliminated, and we don't want to double count, about 1/3 of the pairs remain. So the number of pairs divisible by 5 and not 3, we could represent that as k sub 5 of n, approaches 1/3 times 2/5 times the number of pairs in p sub n as n gets very large. And the number of pairs not divisible by 5 or 3, we can represent that as pi sub 5 of n, is equal to pi sub 3 of n minus k sub 5 of n, and this approaches 1/3 times 3/5 times the number of pairs in p sub n as n gets very large. Next, we eliminated all the pairs where the x or y component is divisible by 7. So in this case, we have 19, 21, 21, 23, 33, 35, 35, 37. And notice that for every group of 7 pairs, we're eliminating 2 pairs. So about 2/7 of the pairs are divisible by 7. But to avoid double counting, we have to multiply by 1/3 and 3/5. So the number of pairs divisible by 7 and not 3 and 5 is k sub 7 of n equals 1/3 times 3/5 times 2/7 times the number of pairs in p sub n. And the number of pairs not divisible by 7, 3, or 5 is pi sub 7 of n, and that equals pi sub 5 of n minus k sub 7 of n, and that works out to 1/3 times 3/5 times 5/7 times the number of pairs in p sub n. And 7 is as high as we need to go because the next higher prime number is 11, and 11 squared is 121, which is greater than our endpoint of 59. So the remaining pairs are twin prime pairs. So for large n, the number of twin prime pairs can be approximated by the following equation. Pi sub 2 star of n equals the number of pairs in p sub n times the product of p equals 3 up to the square root of n of p minus 2 over p, where this product is over prime numbers. And if we define this product portion of the equation as the function w sub n, the equation simplifies to pi sub 2 star of n equals the number of pairs in p sub n times w sub n. So the next thing I did was I plotted my estimate, pi sub 2 star of n, and compared it to the actual number of twin primes pairs less than n. Okay, and here are the results. This blue line here is the actual number of twin primes less than n, and this red line here is my approximation, pi sub 2 star of n. And as you can see, for n less than 5,000, my estimate slightly underestimates the number of twin primes less than n. But as n gets large, here on the right, I plotted for all values of n less than 50,000. And for n less than 50,000, the curves line fall right on top of each other. Also notice that my function pi sub 2 star of n is jagged. It has this sawtooth shaped curve here. And this is because the w function changes in a stepwise fashion. Okay, so here's a picture that explains this. For values, when n goes from a prime number squared minus 2 to a prime number squared, the value of this w function changes. A new term is multiplied by with w sub n, and this causes the curve to drop. Okay, and then for values of n equal to p sub I squared up to p sub I plus 1 squared minus 2, the curve increases with a slope equal to the number of pairs in p sub n. And then when n becomes p sub I plus 1 squared, a new term is added to the w sub n function and the curve drops. Okay, so I know that point between points B and point C on this graph, that the pi sub 2 star of n increases with a slope equal to the number of pairs. But if I can prove that point D is always greater than point B, then that will prove that pi sub 2 star of n increases indefinitely. Okay, so in order to prove this, I need to get the w function of p sub I plus 1 squared in terms of w of p sub I squared. And if we examine the w function, we can see that w of p sub I plus 1 squared equals p sub I plus 1 minus 2 over p sub I plus 1 times w of p sub I squared. Okay, let's define this function delta pi sub 2 star of p sub I equal to pi sub 2 star of p sub I plus 1 squared minus pi sub 2 star of p sub I squared. Okay, so if we substitute, we get delta pi sub 2 star of p sub I equals the number of pairs of p sub I plus 1 squared times w of p sub I plus 1 squared minus the number of pairs of p sub I squared times w of p sub I squared. And since this w of p sub I plus 1 squared can be put in terms of w of p sub I squared, we get delta pi sub 2 star of p sub I equals the number of pairs of p sub I plus 1 squared times p sub I plus 1 minus 2 over p sub I plus 1 times w of p sub I squared times the number of pairs of p sub I squared times w of p sub I squared. And then we factor out the w of p sub I squared and we get this. Delta pi sub 2 star of p sub I equals w of p sub I squared over 2 times this mess here. Okay. So to minimize delta pi sub 2 star of p sub I, we need to minimize this term here. To do this, we have to find the smallest value that p sub I plus 1 could be relative to p sub I. Okay, and the lowest that p sub I plus 1 can be is p sub I plus 2. So substituting p sub I plus 2 in for p sub I plus 1, and then simplifying, we get this. Delta pi sub 2 star of p sub I equals w of p sub I squared over 2 times 2 p sub I plus 6 over p sub I plus 2. Okay? And as p sub I gets large, this term here gets very small. Okay? So we can ignore this term here and change the equal sign to a greater than sign. So delta pi sub 2 star of p sub I is greater than p sub I times w of p sub I squared. So this is the lower bound on delta pi sub 2 star of p sub I squared. Okay. So I plotted this lower bound on delta pi sub 2 star of n and compared it to delta pi sub 2 star of n. And you can see this orange line is definitely the lower bound. This blue curve here does not go lower than this orange line. Okay. So now, if I can prove that the lower bound on delta pi sub 2 star of p sub I is greater than or equal to 1 for all p sub I, then this proves that my curve pi sub 2 star of n increases indefinitely. So I'll prove this by induction. Okay, so base case, I use p sub 0 equals 3, and I substitute that for p sub I, and I get delta pi sub 2 star of 3 equals 3 times w of 3 squared, and this equals 1. Okay, so next I assume that delta pi sub 2 star of p sub I is greater than or equal to 1. And I'm going to prove that delta pi sub 2 star of p sub I plus 1 is greater than or equal to 1. Okay, so delta pi sub 2 star of p sub I plus 1 is p sub I plus 1 times w of p sub I plus 1 squared. But I know that w of p sub I plus 1 squared can be put in terms of w of p sub I squared. So substituting this for w of p sub I plus 1 squared and simplifying, I get delta pi sub 2 star of p sub I plus 1 equals p sub I plus 1 minus 2 times w of p sub I squared, and then multiplying and dividing by p sub I, we get delta pi sub 2 star of p sub I plus 1 equals p sub I plus 1 minus 2 over p sub I times p sub I of w of p sub I squared. And this term here is the same as delta pi sub 2 star of p sub I. And since we assumed that delta pi sub 2 star of p sub I is greater than 1, that's greater than 1, and p sub I plus 1 minus 2 over p sub I, this is always going to be greater than or equal to 1, then the product must be greater than or equal to 1. Okay? Since delta pi sub 2 star of p sub I is greater than 1 for all p sub I, this proves that there is at least one twin prime pair between p sub I squared and p sub I plus 1 squared. And this means that my function pi sub 2 star of n goes up indefinitely. And because this function approaches the twin prime counting function as n gets larger, this proves that there are an infinite number of twin primes. So I was very happy when I made this proof, and I showed it to a mathematician, and he wasn't convinced. There's just one little problem. I've proven that pi sub 2 star of n goes up indefinitely, but pi sub 2 star of n is not equal to pi sub 2 of n. There's a difference, an error. And I have to prove that the difference between pi sub 2 star of n and the actual twin prime counting function, pi sub 2 of n, is small. Small enough so that any increase in pi sub 2 star of n is not offset by the error. So to determine the maximum difference between pi sub 2 star of n and the actual twin prime counting function, I looked at how my pi sub 2 star of n was derived. And in the derivation, I approximated the number of pairs divisible by 3 as 2/3 p sub n, and I compared that to the actual number of pairs divisible by 3. And this maxes out at 1 1/3, and this occurs when p sub n is 2, 5, 8, 11, etc. Okay? And then I did the same for number of pairs divisible by 5. I approximated the number of pairs divisible by 5 as 2/5 p sub n, and I compared that to the actual number of pairs divisible by 5, and this maxes out at 2 when p sub n is 5, 10, 15, 20, etc. And then I did the same thing for 7. I approximated the number of pairs divisible by 7 as 2/7 times p sub n, and I compared that to the actual number of pairs divisible by 7, and this maxes out at 2 2/7. That's 2.285714, and this occurs when p sub n is 8, 15, 22, etc. So the maximum error for a given prime number p can be determined by the equation E sub p equals 3p minus 5 over p. Okay? So for example, if p is 3, 3 times 3 is 9, minus 5 is 4, 4 divided by 3 is 1 1/3. So E sub 3 is 1 1/3. If p is 5, E sub 5 is 3 times 5 is 15, minus 5 is 10, 10 divided by 5 is 2, so E sub 5 is 2. E sub 7 is 3 times 7, which is 21, minus 5 is 16, divided by p divided by 7 is 2 2/7. So E sub 7 is 2 2/7, etc., etc. So the maximum difference between pi sub 2 star of n and pi sub 2 of n, E max sub n, is the sum of p equals 3 up to the square root of n of E sub p, where the summation is over prime numbers. And this works out to be less than 3 pi of the square root of n, where pi is the prime counting function. So the next thing I did was I plotted pi sub 2 of n, the actual twin prime counting function, and compared it to pi sub 2 star of n plus or minus E max of n. Okay, and here are the results. This gray line here is the actual twin prime counting function, and this blue line here is my approximation, pi sub 2 star of n, and these red lines are plus and minus E max of n, and as you can see, pi sub 2 of n lies comfortably between plus or minus E max. And since pi sub 2 star of n increases, like this p sub n increases linearly with n, and this w sub n decreases with the log of n, pi sub 2 star of n increases at a rate of n over the log of n, whereas E max of n increases at a rate of square root of n over log of the square root of n, according to the prime number theory. So pi sub 2 star of n is increasing at a much faster rate than E max of n. Therefore, this proves that there is an infinite number of twin primes. Okay, so in summary, the function pi sub 2 star of n was derived to approximate pi sub 2 of n, the twin prime counting function. And it was proven that there's at least one twin prime pair between pi sub 2 star of p sub I squared and pi sub 2 star of p sub I plus 1 squared. Therefore, pi sub 2 star of n increases indefinitely. Then it was proven that the maximum difference between pi sub 2 star of n and pi sub 2 of n is less than 3 pi of the square root of n. And since 3 pi of the square root of n increases at a much slower rate than pi sub 2 star of n, there are an infinite number of twin primes. And here is the link to my paper, The Definitive Proof of the Twin Prime Conjecture in VIXRA. Please read it. It has all the nitty-gritty details that were not covered in this presentation. Make sure you're reading the latest version, and here are links to my other papers. And here are my references. And I leave you with the Watanabe conjecture number 1 that states, for any integer n, there is at least one twin prime pair between n squared and n plus 2 quantity squared. For example, for n equals 2, there's at least one twin prime pair between 4 and 16, and in fact there's 2. There's 5 and 7, and 11 and 13. For n equals 5, there's at least one twin prime pair between 25 and 49, and in fact there's 2, 29, 31, and 41, 43. And I'll leave this conjecture for you to prove. Thank you for watching.